Hi class, I'd like to redo problem number 34 from section 2.5 so you'll have a video of this particular problem we did in class. So we have the limit as x approaches minus infinity of x plus the square root of x squared minus 5x. When we were looking at asymptotes of algebraic functions, we found that one rule that was really cool, if we could express our limit such that we had a ratio, a numerator and a denominator. And here we really don't have a ratio. So what we'll do is we'll rewrite this over 1, and then we'll rationalize the numerator, and we'll do that by multiplying by the conjugate. So instead of having a plus, we're going to have this same expression with the subtraction symbol. So we'll have x minus the square root of x squared minus 5x, but we must do the same in the denominator. So x minus the square root of x squared minus 5x. Now when we do the multiplication in the numerator, we found that the reason why we multiply by the conjugate is because the middle terms are going to cancel. So if you multiply these two terms, the inside terms, you get x times the square root of x squared minus 5x. And then when you multiply the outside terms, because of this minus sign, you're going to get x times the square root of x squared minus 5x, but it's going to be a minus x times the square root of x squared plus 5x. So that when you add the middle terms and the outside terms, what happens is they cancel, and you just get 0. And that's the whole purpose of multiplying by the conjugate and why you want those opposite signs. And so then all you're left with is the first term, x times x, which gives us x squared, minus the square root of x squared minus 5x times the square root of x squared minus 5x, which is equivalent to x squared minus 5x quantity squared. And then remember, we got to keep that denominator of x minus the square root of x squared minus 5x. Now that we have a rational expression, our rule was to divide by the highest power in the denominator. And here we have an x in the denominator, and here we have the square root of x squared minus 5x. But as x decreases without bound, this 5x is negligible because the squared is going to take over. If you think of a million squared compared to 5 times a million, it's not as much. Well, think of it a trillion, that's 12 zeros, squared, that's 24 zeros, compared to 5 times 12 zeros, 1 with 12 zeros, you can see that this one's going to take control. So it's almost as if this expression really, the subtracted 5x, isn't going to contribute once x gets very, very small. I should say more and more negative, not very, very small, but more and more negative. So we can think of the square root of x squared, and I'll do this in a little thought cloud, is what's going to be the highest power when you look at the radical part of this expression in the denominator. However, what does that simplify to if x is decreasing without bound? And we found that it's equal to the opposite of x. And let's go ahead and take a look at y. Let's look at some negative values for x. For example, let's just take negative 5. So we have the square root of negative 5 squared. When we take the square root of negative 5 squared, it's equal to the square root of 25. But that's just equal to 5. But 5 is just equal to the opposite of negative 5. And that's what we have here is the opposite of x. And x was the negative 5. So that's what we find when we have the square root of x squared if x is negative. So let's write out the form. So the square root of x squared is equal to x if x is greater than or equal to 0, or the opposite of x if x is less than 0. And if you think about it, the square root of x squared, a lot of times we refer to that as the distance, which is the absolute value. And the formula for the absolute value is the same. It's saying that it's equal to x if x is greater than or equal to 0, or the opposite of x if x is less than 0. And we do it all the time. If you take the absolute value of negative 5, we just say 5. We don't write the opposite of negative 5, but we know that the opposite of negative 5 is 5. So we could write it as minus 5, which is the same as 5. So in summary, for our case, the square root of x squared is going to equal the opposite of x if x is less than 0, and that's the case whenever x is approaching negative infinity. Then if we multiply both sides by negative 1, then we'll have the opposite of x squared is equal to x. And that's going to be helpful when we do that substitution, when we're trying to simplify that rational expression. So now we have the limit as x approaches minus infinity of x squared minus the square root of 5x, x squared minus 5x, that quantity squared all over x minus the square root of x squared minus 5x. And again, we notice that when you square the radical, that eliminates the radical, I say freeing the radicand from prison. We just have to be careful of one little thing. We want to make sure that we're subtracting the whole expression x squared minus 5x that was part of the radicand, or that is the radicand. So we want to make sure we put parentheses and subtract that quantity, otherwise we'll get an incorrect answer. So when I distribute the minus sign, I'm going to get x squared minus x squared, and then when I subtract the subtracted 5x, that's going to leave me with a positive 5x. So I have the limit as x approaches minus infinity of positive 5x all over x minus the square root of x squared minus 5x. And now I'm going to divide top and bottom by the highest power in the denominator, and the highest power in the denominator is x. So I'm going to have the limit as x approaches minus infinity of 5x over x all over x minus the square root of x squared minus 5x over x. And I can do that because when I divide by x top and bottom, it's equivalent to multiplying by 1 over x over 1 over x. And that expression is equal to 1, except when x is equal to 0. And we don't have to worry about that because we're decreasing without bound. That's not near 0. So dividing by x top and bottom is equivalent to multiplying by 1 over x over 1 over x, and it's okay to write it in this form. Then we have the limit as x approaches infinity of 5 over 1 minus, and this is where our substitution is going to come in handy. We had that x was equal to the opposite of square root of x squared if x was less than 0, and that's the case when you're decreasing without bound. So then we have the square root of x squared minus 5x all over the square root of x squared, and then we have that minus out front. So we have the limit as x approaches minus infinity of 5 over 1 plus. And now that I have both radicals, I'm going to rewrite this as a single radical. So it's going to be the square root of x squared minus 5x over x squared. And then when I simplify, that'll leave me with limit as x approaches minus infinity of 5 over 1 plus the square root. And when we take that x squared over x squared, that's going to simplify to be 1 minus 5x over x squared. So that'll become 1. So we have the limit as x approaches minus infinity of 5 over 1 plus the square root of 1 minus. And here we can cancel the x in the numerator, and that'll leave me with an x in the denominator. So that'll have 5 over x. And then we know the limit as x approaches minus infinity of a quotient is just to take the limit of the numerator and then the limit of the denominator. And then we can take the limit of these two things added up. And then we could also take the limit of what's inside. We could write all that out, but just to save us some time, I'm totally okay if you just say, hey, I know that as x approaches infinity, that minus infinity, that this expression in the denominator 5 over x is going to go to 0. So then we're just left with 5 over 1 plus the square root of 1, which is equal to 5 over 1 plus 1, or 5 halves. So the limit is equal to 5 halves. So I hope this video on number 34 from section 2.5 has been helpful for you.